Hey everyone, this is part 2 of building GPT from scratch. And in the previous video, we have already built a GPT, we have completed the architecture building of the GPT from scratch. The model was complete. And now we are going to write some data loading part, the data primitives, and we'll be training our custom built GPT. And let's see how it goes. And I can assure that now the video will not be 1 hour long. So this will be a smaller video. Okay, so this is where we left in the previous one, and now I need to write my data utils. So the first thing that I would need is OS, then I would be needing, I think, torch for sure, and I would be needing my data sets from datasets. So this is basically, I think, pip install datasets. This is not coming directly with torch. So from datasets, I'll be importing load datasets. I think it's dataset, yeah. Okay. Then I would be needing torch.utils dot data import data loader and data set. I think data load. Okay, wait, spelling is data load. Yeah, data load. Okay, fine. Okay, from again, this is from transformer, because I will be using that. Okay, so I would be using the GPT-2 tokenizer. So I need this transformer library again. So pip install transformer and then pip install datasets. So these two pip libraries have to be installed. Apart from that, I think we won't be needing anything else. So from transformer, import auto tokenizer, I guess that's the spelling. All right, cool. So we would be creating a wikitext class, because we need Wikipedia dataset. So we'll call that wikitext dataset, and now this will import data, this will inherit dataset class of torch.utils or data, and this will have my tokenizer. Oh, sorry, I need the initializations, so I'm just copying this to this, and I still need tokenizer. So I'll pass tokenizer. I will pass sequence length. Yeah, I think that's it. I don't need anything else in the dataset. It's not GPT anymore. Self.tokenizer. So this will be tokenizer that I am passing. Oh, sorry, this is inside this. Yeah. Okay. Then self.sequence length would be sequence length. All right. Then tokenized data will be tokenizer, and this would take texts. I need return tensors is equal to pt. Truncation. Wait, what's the problem? Oh, I didn't pass texts. Okay, I need truncation to be true, and I need padding as true. All right. Self.input IDs, which is usually the case. Like usually these tokenizers give you input IDs. So self.input IDs from the tokenized data, I'll fetch this input IDs. This is a very typical Hugging Face transformer, Hugging Face tokenizing mechanism, that it will just give you input IDs, and I'll just flatten it out. Then I need the length. I'll define my length. So basically this is the typical way how we define custom datasets in PyTorch. So we will first initialize everything. Then we will have a length function and a get function, basically get item function. So in the length, it will be just self, and yeah, that's it. I will just return length of my self dot input IDs, and that will be divided by self dot sequence length. So I don't need, like, I don't want to return entire input IDs. I want to return in the I need like I don't need any of those tokenized documents that are greater than the sequence length, right? So that is why the length is fixed till sequence length. Now def get item, sorry, yeah, get item, okay. Then self and index. Oh wait, what happened? Oh sorry, I think I pressed run. Okay, get item self dot index. Now my start index will be index multiplied by self dot sequence length, and my end index would be just addition of start index plus self dot sequence length. Okay, then my inputs will be self dot input IDs from start index till end index, and my targets are basically, okay, so these are my inputs. So basically what I did was I just gave it an index. It will multiply it by the sequence length, and it will, when it will add the sequence length to it, so it will give me a window which is of sequence length width, right? And from huge inputs, like from this whole huge input matrix, input vector basically, I will just let's say the index is 55, so I will go to 55, add the sequence length to 55, let's say that's 10, so from 55 to 65, I just need that input. So that is captured in the inputs at line 27. Now my x, so basically the x is basically the training data, right? The training batch, or the training sequence, not the batch even. It's a training sequence right now. So that will be inputs from 0 till -1. Like I don't need the last token. I don't need that, because I have to shift this input by 1 to get the target. So y, which is my target, is inputs, but it will start from 1 till the end. So notice that I'm still having the sequence length, but but the input is sequence length -1, and even my target is sequence length -1. Does that make sense? Because I truncated this from 55 to 65, I truncated by 1, so that when I'll shift by 1, they both are of the same size. All right, so I think this class is done. Okay, I won't collapse this. I'll just keep it here. Now I need another class, which will be, no, I think, yeah, okay. So I don't need class now. I just need a function which will create my data loader. So create data loader, and this will have my batch size, sequence length, and the name of the tokenizer. So tokenizer name, which is equal to, I think it's in the, yeah, I think it's in the small letters GPT-2. Okay, I haven't opened the reference code, so I might make a mistake here. I'll quickly open as soon as I get any doubt. Or just give me a second, let me open it so that there is no mistake. Yeah, here it is. Okay, yeah, it's small GPT-2, so we are fine. So data set is equal to load data set, and I need to copy this because this thing for sure I cannot remember. So this is wiki text raw version, like version v1, and I need to also copy this thing because I cannot remember this. Like some things like it's really hard to like remember. So every time what I do is I usually search either ChatGPT or Stack Overflow and get all these syntax. So let me quickly explain what I did here. So at line 34, I just loaded my wiki text, and this gives me 3 dictionaries. One is train, one is valid, and one is test. And each of those dictionaries have text. So basically this is just raw text, right? And then the tokenizer, oh wait, tokenizer name should be correctly given. Yep. Sequence length. Okay, sorry, I didn't do that. Wiki text data should be like this. All right. So line number 36 is just calling that tokenizer by like just calling the particular GPT-2 tokenizer, and since it doesn't have a padding token, so I'm just using its end of token to be same as the padding token, so that if you have any sequence that is less than the sequence length, then you just add, or you just pad that particular token, and in our case that is just the end of the token, end of the sentence token. Now once this is done, I'm just stripping all those texts which are just blank spaces or just blank lines. I don't need that. And line 39 will just call this wiki text dataset that we created, and we have the text, we have the tokenizer, and we have the sequence length. So when we call this particular object, or when we call this particular dataset, we pass tokenizer through it, right? So now this tokenizer is nothing but the tokenizer of GPT-2, and it will tokenize all these texts. And notice these texts are nothing but list of strings. So notice how we created this list of strings, and then we passed those lists into our wiki text dataset, right? So tokenizer is just tokenizing all the strings in the list, and for that we now extract the input IDs, which are the tokenized strings, and we will just flatten that out. Okay, so that are our input IDs, and from these flattened vectors of our tokenized text, we will chop off different sequences, okay, of fixed sequence length. Let's say 256 is our sequence length, and we will truncate it by 1 so that we have X and Y of the same size but shifted by 1, right? So let's say that we have an input sequence of my name is, so the target for my would be name, the target for name would be is, and the target for is would be the name, the noun. Okay, so this is what we are doing. Now once this is done, then we would just create the data loader for it. Oh, just a second. Yeah, we would just create a data loader for it by passing on these tokenized data sets, or basically our custom dataset class. We would pass on the batch size, and we would just pass the shuffle as true, and we would just return our tokenizer and the data loader. Now the point is that why are we returning the tokenizer? because we would need the vocab size to pass into the GPT model, because that vocab size is required for the embedding matrix, right? So that's why we need the tokenizer to be returned. Okay, now let's see what's all is left. Okay, so there are some utility functions which I have written earlier, and I'll just like copy them as it is. They are related to saving checkpoint and loading checkpoints and counting parameters. So let me quickly paste them. So this is nothing fancy. Line 45 is a function of saving checkpoint. Basically, I'm taking my model optimizer, whatever the epoch that I have, and I'm just saving it by the name of checkpoint.pth. So this is pretty easy. Let me press enter here so that it's visible. Okay, in the loading checkpoint, I'm just checking that if the path exists, load the checkpoint, load the optimizer, and return the epoch so that we can start from the epoch that was left, like from where we left off. Okay, so these two functions are pretty easy, like nothing fancy here as well. So we return this. Okay, so count parameters in millions. We are just summing all the parameters of our model, and then we are just dividing it by 1e6 so that we have the parameters in millions. Okay, so pretty simple utility functions. Yeah, I have an interesting function which I wrote, which is called as generate text. Okay, what it does is it will first put the model in the eval mode. It will get the device, it will get the IDs. So basically what I'm trying to do in this particular function is that I will give it a prompt, and it will result into the next predicted output or the next predicted token. And I wanted to like discuss it for like 2 minutes, that how it's done. So basically we have the model on our device and we have the prompt. So all we need to do is just pass that prompt to the tokenizer, and we need the input IDs again, which are nothing but the tokenized version of the strings. And we are saying that do some generation for maximum number of the steps. So let's say that the maximum steps are 3. So basically it will do the generation thrice. And how it will do, let's take a look. So when I pass on the input or the tokenized version of the text to the model, it will give me output, and the output is of the it's of the dimension. Let me clarify here. So the output is of the dimension batch size cross the sequence length cross the vocab. So notice that the sequence consists of all the tokens that are coming in the sequence, and for each token I have my vocabulary. So let's say that the sequence is okay, so let's say that the batch is 16 and the sequence is, let's say, 10, and let's say that the vocabulary is 512. Oh, sorry, vocabulary is 26. Let's say 26 alphabets of English. Now, let's say that we are looking at the 5th alphabet in the sequence, and in the 5th alphabet, we are having this dimension of vocabulary, which is 26. Now, inside this 26 are nothing but probabilities, right? So it is the probability that if you're standing at the 5th index, then what is the probability of the 6th token out of all those vocabulary? So out of all the 26 alphabets, there would be one alphabet that will have the maximum probability, and that will be the next most probable token. So that's what I'm doing. I'm doing a torched.argmax, getting the index, but I need at the sequence dimension, right? At the sequence dimension and at the last of the sequence. So after I finish the sequence, so for example, the sequence was that my name is. So I would go to the last, which is, and in that is, I would have my 26 or whatever vocab size, and I would pick out the torch.argmax, which is the index of the maximum probable token. I will pick that out. That is my next token, next probable token, right? I will concatenate that token to my input IDs, right? And that will become my first generated output. Now, if my input IDs are increasing, so basically I'm kind of writing a sentence. So for example, if I start with the city I live in, if I just have the string, and I will try to write the city I live in is Montreal, which is in Canada. So it will like kind of, it will try to write the whole sentence if the model has understood the semantic representations, all different kind of grammatical rules, all the linguistic rules. So if the model is able to generalize well over language, then it will be able to kind of derive the relations or the most so basically it will output the token in a coherent sense that will make sense to us. And that's what language models do. They don't know anything. It's just that they have understood the representations in such a way that the output that they predict kind of just makes sense because it made sense in the data, right? So that's what I'm trying to do here. Now, once I have done my input IDs for, like once I have done this kind of generation for, let's say 3 steps, then finally I'm just saying that, okay, all these input IDs, all these tokenized versions are still just tokens. They don't make sense to me. So decode them, and Tokenizer has that option. So converting back to the English from your tokenized version is nothing but tokenizer.decode. Okay, and this is my English text, and that's what I'm printing in the end. So I will give it a prompt, run through these steps, and then generate some text. Okay, so this is what this utility function does. Perfect. So I think we have done our data utilities, so that's fine. Now let's try to run everything together. Let's now like stitch everything together. So the first function that we need is train GPT model, and we don't need any arguments. It will be like kind of like all the arguments will be just given by hand. So it will do something. All right. Then I just need to write the main. Okay. I need to import all the stuff now, which is storage. I'm using the Atom with weight decay, which is Atom W. TQDM will be used for just displaying a progress bar. I need to now have all my create data loader, generate text, count parameters, load checkpoint, save checkpoint. So this is all. So line number 5 is the utilities from the data primitives, and I need to import the GPT model from my model file. Nothing more. Now I'll design the parameters, hyperparameters basically. So now I don't need this. Okay, so the first hyperparameter is batch size, and I'm going to put it to 128. So basically batch size will depend on your machine. The machine that I'm working, it's able to accommodate high batch sizes, so that's fine. The sequence length will be 128. I don't want to increase sequence length because increasing the sequence length will kind of increase the amount of time that it takes to train. Okay, number of epochs I'm just keeping at high 30, but we will not sit and wait till 30 epochs. We will just see that how our training looks through like at least 5 epochs maybe. Learning rate, reasonable 1 E minus 3. Tokenizer name is GPT-2, that's fine. Now we'll call at our data loader, and we need tokenizer, and create data loader. We'll pass on the batch size, we'll pass on the sequence length, and we'll pass on the tokenizer name. And let me just quickly check that batch size, sequence length, tokenizer name is the correct order. Okay, batch size, sequence length, yeah, it's the correct order. That's fine. Okay, now I need my model is equal to GPT-2. Yeah, GPT, not GPT-2. So GPT, and let me quickly see what is the order here. So number, okay. Oh, sorry, I closed it. Yeah, GPT here. So vocab size, I won't pass it. So that will be tokenizer. So basically, vocab size is equal to length of the tokenizer, right? That's how that's the total vocabulary that the tokenizer is holding. Okay, then the embedding size is just 768. I think this is the original embedding size in the GPT-1 model. Sequence length is sequence length. Number of layers, I'll just keep it at 2. I don't want to like increasing the number of layers is just increasing the depth, increasing more parameters. So I don't want to do that. I just want to quickly iterate. And reasonable number of heads would be 4. I think that's fine. And put it to CUDA. All right. Ideally, we should detect the device and then place it there. But I know that I'll be training on CUDA. Okay, so let me now have a test string. So we'll now define optimizer and the loss function. Okay, we'll define it later, but we'll have a test string as a guitar is, and we'll let this thing to tokenize and basically generate the text. So this is the generation of the text before training, right? So we'll just add print before training. Okay, and I think in generate text, do I say that it's testing generation for the input string? Okay, so I don't mention that. Is it before training or after training? That's fine. Oops, sorry. So run generate before training, and I'll just give it some formatting. Okay, perfect. Then I need my optimizer, which is AtomW, and the learning rate is 1e minus 3, and the weight decay is 0.01. These parameters are kind of tuned because I've already built this earlier, and I saw that with a very less weight decay, it works, but it gives you quicker results with 0.01 because now you're enforcing more weight decay, so weights are kind of going basically they are diminishing rapidly. So that helps. Then finally we want to print. We also want the parameters to be counted, and let's do that before. Okay, so number of parameters, count parameters in millions, and let's print those parameters. Okay, so this is testing, and yeah, that's fine. Okay, and once the optimizer is loaded, then we would just start, we would call this load checkpoint. So inside this load checkpoint function, we will check that if there is already a checkpoint available, we'll just load it, and we are saving the epochs. So we'll just start it from that epoch, that epoch plus 1. But if there is no checkpoint, we'll just start it from 0. So here the start epoch initially will be 0. Okay, now our training loop starts. So for epoch, now I'm getting excited. So for epoch, in the range start epoch and number of it was number of epochs. Wait, num epoch, sorry. Okay, so first of all, just put model.train. I've done this mistake countless number of times, that sometimes forgetting to toggle between model.train and model.eval. So don't make that mistake. Okay, epoch loss would be 0. Let me just put it to float, and then let me just define a progress bar, which will be like basically just TQDM over the data loader. So I'm just enumerating over the data loader, and like this will help me patiently waiting so that I can see that, okay, this is how the data is getting ingested. Then for batch, index and the inputs, the targets, okay, in progress bar. Oops, sorry. Yeah, so now my inputs, comma targets have to be moved to inputs dot to CUDA, and targets dot to CUDA. Okay, now just call the model. So this will give me log probability model inputs, and the loss will be model.loss and log probs and the target. Perfect. Sorry, targets. Okay, S is missing. Okay, the epoch loss becomes like just added to the loss and dot item. Like loss is still a tensor, and we need to extract the scalar from that. So just dot item will suffice. Now do a backward pass. So basically loss dot backward, like this will compute, like this will do the backward pass, and then optimizer dot step. So again, a bad practice, I didn't do optimizer dot zero grad. This is a really bad habit of me, that the first step should be that optimizer should, like, the gradient should be zeroed out first. That is the principle, that's the rule of thumb. So I should never write loss dot backward. The first step should always be writing the optimizer dot zero grad, and then we should like have the loss dot backward and then the optimizer dot step. I think one of my colleagues, he always uses this. Like, firstly, just write the optimizer dot zero grad, get it done, so that it never creates any ruckus afterwards. Okay, we have the loss dot backward, optimizer dot step is fine, and then we would just add a small printing that if the batch is a multiple of 200s, then just oh wait, batch index is not getting printed. Oh, sorry, it's batch IDX. Now that's fine. Okay. All right. Once this progress bar is done, so basically this would mean that we have iterated over the data loader, and yeah, so now I will be just printing. Oh wait, I already have this, so I'll just copy this down. I need it outside the for loop, so let me collapse this, and once this is done, I need the saving as well after every checkpoint. Okay, so this is fine. And finally, once my for loop is also done, then just print that model is trained. All right, so we have completed our yeah, we have completed the loading part, we have completed the training loop, and now the moment of truth. Okay, so Python run.py. Okay, let's hope that there's no mistake. Oops, no module name transformer. Wait, it says in the data utils from transformer. Interesting. Oh, transformers. Sorry. Okay. Let's try it again. This is always the case. I just hope there are no more silly errors. Okay. Truncation is not trunction. Oh, my bad. Truncation would be here. Okay. All right. Okay, no more errors now. Come on. Ooh, okay. What does it say? NN has no attribute. That's strange. We are in the layer norm. NN.module. Reset params. NN.init. Oh, it's init dot. Sorry. Okay. Come on now. So that's what I'm telling. These kind of small mistakes always come up. Okay. All right. Wait. Where did it go wrong? It went wrong in line this. Okay. So MHA object. It's KW, VW. Okay, that's fine. QW, it should be KW, and it should be VW, and then it should be WO. Okay, that's fine. All right, now it's frustrating and embarrassing at the same time, but that's what it is. Let's see. Too many values. Okay, this is still manageable in the merge heads. Okay. Yeah, in the merge heads we will have 4 values, so that's fine. Let's see. Okay, it's taking time. Okay. Okay, let's put it at NH in H. So if I use this, then it will be NH. Logically, it should be correct, right? That's interesting. How did merge head get wrong? We are permuting. Okay. Is it because it's not contiguous in the merge heads? I think so. That's the problem. Okay, let's try this. Oh yeah, because I think permutes, when we do permute, then the tensor is reshaped in such a way that it might lose its contiguousness. So yeah, okay. Oh, okay. Linear. Where did we go wrong? I've got linear, so the call is in the embeddings. Okay. All right. And there is a linear that's going in the layers, the block. That's fine. Okay, so let me pause the video here and let me quickly resolve these small issues, and I'll resume just in like in the next part. All right, so I've resolved the errors. There were two silly mistakes, so let me quickly go through them. So firstly, there was a missing return in the data utils, basically in the wiki text dataset. So there was this statement missing, which was basically like not giving any data in the data loader. So this was wrong. Then there was this +1 missing as well. So basically, I told you that we were truncating the sequences, but the sequence length has to be maintained. And I don't know why I said that we are shortening the sequence length by 1. So we need to add that 1 as well, because if we don't do that, then our sequence length will become shorter by 1, and our matrix multiplications in our model will just go haywire. So this was one mistake, like two mistakes in this Wikitext dataset, and there was one mistake in the model.py file, and it was in the merge head. So you remember that in the while I was writing the code, the x dots, like I wrote this nh after the sequence.length. So I was emphasizing that we should be careful in writing this, and I myself made a mistake. So apologies for that. So the number of heads have to be before the sequence length. So we don't care about these dimensions because we already have stored those head dimensions we have already stored the head dimensions and the number of heads. So that's fine. And I hastily wrote just like nh into h. So I shouldn't have become nervous. Also, one more thing. Permute does not guarantee that it will give you a tensor that is contiguous, right? So it can happen that the view can destroy the memory allocation which is contiguous, and we don't want that. The memory has to be contiguous. So whenever we have permute, then contiguous have to be applied. So I think it's not done here as well. Okay, it's okay in the split head function, because the permute, like after the permute, there is no calling of view function. So if you want to call the view function after permute, you have to you basically have to call contiguous on the permute. All right, you must have looked at the output. So it started running. Now let us quickly wait for the moment of truth. Now I think now there are no errors. Okay, okay, so the first output that it says is that a guitar is teach, rugged, ren, like something garbage. So basically this word that came, it has no meaning. So now we will wait for the model to get trained for some epochs, and I'm going to pause the video and I'll resume once I have at least some kind of good some kind of coherent results. And as soon as I have them, I'll resume our video and share that with you. So now let's wait for some time. All right, so I've been waiting for like 20 minutes, and I wanted to show you the outputs right from the start. So when the model is not trained at all, so we have like we just have garbage from the model. So it just says that a guitar is, and after that the prediction is just like just garbage tokens, randomized tokens basically. But then I had some issues with the allocation of the GPUs, so I got 2 epochs saved, and now I have new allocation for the GPUs, and I'm starting from 3 epochs, like the third epoch. So now I can see that there is some coherence in the words. So it is not completely garbage. It is still some English words, but it is not at all like it doesn't make sense. It's like a guitar is a member of, a guitar is something white, again a member of, high school, fictionalized. But now you see that in epoch 4 there's a song. So now guitar is like this context is moving into song and something like that. So we got another song by, a guitar is used as maybe an instrument. I don't know. A guitar is composed of, okay, grade 2 song by. So it's heavily getting biased towards this phrase of a guitar is a song. Maybe this bias would be removed in further epochs, and we can see that the average loss per batch is decreasing as we increase our epochs. So when epoch 4 got completed, it's 66. When epoch 3 got completed, 74. We don't have, I think we don't have the results for epoch 2 because it was it was downloaded. So for a 130 million parameter model, we are kind of getting closer to the coherence part, but it's still far-fetched. So this shows that, of course, and one more thing, this is not hyperparameter tuned, so there would be some effects of those as well. That is the model wide enough, or is the model deep enough? But we are still getting the essence that your average loss is decreasing, and somehow the model is able to give you some coherent words. Of course, as the number of epochs will get increased, the coherence will also increase. So I guess this proves us that what we built is practically correct. Oh, now it says a guitar is bagged annually. So this is interesting, and of course this will require like at least an hour of training. I'm just using like 1 GPU. I'm not using any kind of distributed training, so yeah, this will take time. But anyways, I guess we can now safely conclude that we have built a GPT model from scratch, and we have not used any of the Torch primitives or any of the Torch libraries except the basic building blocks, and we have applied that GPT to a real-world data set of wiki text, and we are witnessing that it works, and we have now understood that what are the intricacies of different layers, attention, how to build a transformer block, how to write a custom loss function, and all the nitty-gritty details. So I would now like to conclude. Oh, it says a guitar is a set in. Okay. I'm just waiting and expecting that when will it say that a guitar is a musical instrument or something like that. But I guess it will take time. Alright, so I like to conclude this video, and maybe next weekend I'll try to like run, or maybe like give an overview of how distributed training works. So let's see. Stay tuned, and I hope everybody who is watching this video liked it and got something to learn about, or just got their basics refreshed. All right, so see you next time. Bye.